slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a
Learning life cycle all the way from data preparation, from loading the data itself, doing what's called feature engineering, doing what's called exploratory data analysis or EDA. Then we went further and started building our own machine learning algorithm. So we started off with the classification algorithms, and the first one was logistic regression. Under each of them, we saw what it meant, how is it generated, how does it work, and the mathematical intuition behind each of them. And we're able to see that in the previous sections. Okay. We can also plot the scatter plot for each of the model. Like here, tukona scatter plot of logistic regression. We can get this. Okay. For the confusion matrix, we can also have this. I explained the confusion matrix in the earlier section, what it means. And the next thing was to check on the performance matrix evaluations like accuracy score, what does precision recall function means, what's F1 score, what is weighted graph, and where are they being used. And that's what we want to talk about today. We move to decision tree as well. We check for the classification report, precision recall function, F1 score, micro average, weighted average, and support. I'm going to break down all this to you, what they mean, where are they being used, and what's the meaning or the derivation behind them. What's even the mathematical computation behind them. So you get to understand how to interpret them and work them with your data. Then we want to move to the linear regression where we will be able to predict a given score. Like let me navigate down, down, down to regression algorithms. So we have what's called linear regression. So the same applies. What it means, when is it used, what is the mathematical intuition behind it, okay? And we're going to do it by an example, line of code. Then you are able to predict a value. Like here, I'm going to predict for the value 5. We're having an array of the answers. So this array maps to what was there originally in my data set. So I'm able to see that. We can also check the draw a scatter plot to confirm or to compare the of out of the math score, what is the actual versus the predicted scores for the math score. So you are able to see that as well. Together with what's called residual plots. I'll share with you all this. Okay, I'll share with you all this before the end of the class. We will have a look at it. So that's all about what we've been doing under supervised machine learning. What we want to discuss today is the performance matrix evaluation. What does precision mean? What does accuracy mean? What does F1 score mean? Okay. And I think if you have no question at that point, we can dive into the evaluation matrix. Do you have any question based on what we did before, Mr. Dennis? All right, that's great. Now let's break it to you down. I've been promising this to you. Let's break this down. Okay, I want to go through the data set overview, what we've been doing, how we split our data, how we train our data, and how we're checking on the performance metrics. Okay, what each of them mean. We can go ahead and even deploy our model. By what school we use what's called H5 files. Okay, or you do we call the pickle algorithm to download the entire algorithm plus its history. Okay, and you'll be able to see that in the coming days. Now with me here, I have a document showing us all the performance analysis. Okay, use the student performance data itself, student performance.csv, which we had 1,000 observations. Okay, or 1,000 entries, together with 8 features. Features, you can call them columns. You can also transform them to what is called variables. And we found that the overall accuracy was at 89%. This is shown by 0.89, which means 89% accurate, which is perfectly fine. Which is perfectly fine. We all agree that a machine learning algorithm accuracy must be ranged between 85 to 98 at most. 100, think twice about 100%. So 85 to around 98, 99. No problem with that. If 100% is either your model is overfitted or your data is small. If your data is small, you will accept that. But if you have a huge amount of data, like thousands, achieving 100% accuracy, there might be a problem with that. So you can opt to do what's called hyperparameter tuning, or you can change the model to see how each of them performs. Now, this is the overview of the dataset that we had. It contained 1,000 student records with 8 columns, okay, 5 categorical and 3 numerical values. So there are no missing values in our data. Remember during our data preparation step where we check for data.isNull.sum, we had 0. So each and every column had 0 missing value. Hope you remember that. Now we have 5 categorical column, that is gender, race, ethnicity, race or ethnicity, parental level of education, lunch, test preparation course. So those are the first 5 categorical variables. Then we had 3 numerical variables, like for writing scores, math score, and reading score. That's an overview of the data that we use to do the logistic regression itself, where we are checking out if a student, we have to predict whether student has passed or failed. Okay. So in summary, no null values were detected in any column. So the dataset is clean and ready for modeling without any imputation. So you have no doubt there were data, no missing values, no duplicates. We are sure that our model will be working with exact data without any bias. Now, this was the data preparation step that we carried out. Before we fitted the model, 2 engineering features were created from the raw scores. 2 new features were created, or what is called feature engineering. We were able to come up with a pass column, and we also created a new total column. And I think you are able to remember that. The first column that we came up with is the pass one, that was the target variable. Now, because we're working with the logistic regression, we transform where math score is greater than 50. Where math score is greater than 50, we label that as 1. Otherwise, we label it at 0. Why? In logistic regression, we are comparing two values, zeros and 1. 0 and 1 for you to come up with the exact classification. So let me take you back here in our data. Let me take you to our logistic regression. Okay. Yeah, so here is it. You can see here we have blue against the, is it yellow dotted line, meaning my data has been classified into 2 prediction. We have the failed, which is classified by the purple color, and then you have the yellow color for the Sinwar passed above 50. Somewhere here, above 50, these are classified as failed, as passed, while below 50 here has been classified as failed by the purple color. How people say that, Mr. Dennis? Can you see that on my side? Yeah. So I'll share with you this particular. I plotted this to show you exactly how my result has come out. The classification itself for the pass against the fail. And this here is where we stopped, where you saw the precision, recall, F1 score, and then the rest. And then you plot that, you'll see visually how your data has been classified. So the top one here is the pass, down one here is the fail. Fail is denoted by 0, pass is denoted by 1. If you are keen enough, you will be able to see a sigmoid curve out of this. There's a sigmoid curve out of this. What is the sigmoid curve? Something of this sort. Okay, this is a linear one. Then it's a logistic regression. The outermost predicted as 1 will be at the top. Those ones are predicted at 0 should be at the bottom. And that's exactly what you have done over here. All those predicted as 0 will be down here, while all those are predicted as pass or 1 will be at the top. So if you draw a sigmoid curve right over here, you'll be able to see that as well. Okay. So this is the graphical implementation, and this is now the explanation itself. It must not be perfect though, but most of the data with the one will be at the top, while those data with the zeros are or fail will be at the bottom, right over there. So that's what's called a sigmoid function, giving up the sigmoid curve. And you also have the mathematical computation or the mathematical intuition, how it's coming up. So let's go back here and see. So we have the columns for pass and we have the column for total as well. Now we went ahead to split our data into two segments. Okay. After coming up with new features for total scores and for pass, we went ahead and split our data into two portions. Why? This very essential step when coming up with a machine learning algorithm. At one point, you might require to test your data, how to test the performance of your data or the performance of your algorithm on your data. So for us, we had 1000 records whereby we split our data into training set and validation set. So this particular line of code here was able to do that. X train, X test, Y train, Y test, okay? And then we got the train test split. The train test split is a function itself where you have to call. So let me take you back into that right over here. Train test split is a function that will help you to split your data into the training set and the validation set. So you have to import that here from sklearn with model selection. You have to import the train test split. That will split your data into training set, which is normally 80. Some books can use 70, while validation set is normally 20% of the entire data. Once you call that, you'll be able to split your data into two sections. 0.2 means 20% testing, that's test size, while 0.8 is 80% of the training set. And we discuss that into details. So, ideally speaking, 800 observations were used for training, while 200 observations were used for testing. This has been done by reshuffling. And how do you reshuffle that? You call what's called a random state. Random set of 42. This will help you reshuffle your data to avoid the aspect in human term, you can call it cramming aspect. To avoid that. So it will learn through the data randomly, without any biasness. So assume that maybe in your data you arrange it such that all those that with higher values come at the first, while those with the lower values follows. No. If you do that and you don't specify the random set, your machine learning algorithm will maybe only give priority to the high value results. will give priority to the high value entries. So to avoid that, you have to call the random set itself. So random set is called 42. This will give you a random or reshuffling of your data during the training process. We also saw the descriptive statistic of your data, which gives you summary statistics for three numerical columns. That is the math score, reading score, and rate score across all the entire 1000 students. And we're able to see that as well. Okay. Now, after doing that, we notice one thing. There's a class imbalance. There's a class imbalance. And tomorrow we'll see how do you manage class imbalance where you are having a class imbalance. For us, for instance, here, we have found that 20% 0.5 students have failed. Less than 5% of the students have failed, while 87% of the students has passed. So there's that imbalance. There's no that middle point say, oh, 50% of the students has failed, 50% of the students has passed. No. Majority of my students have passed. So there's a class imbalance. Fail versus pass. The test set, okay, which contains 200 records, contains a significant class imbalance, and you're able to see that. The proportion of pass students is much larger than the fail students. And that one you can see via even during the training process in the chart here, you are able to see that majority of the students, the yellow lines are so much. These are the students who have passed. That's so much, while those who have failed are quite little. So there's that class imbalance. I hope you're able to see that, Mr. Dennis. By show of thumbs up if you can see that. Great. Now, we denoted 0 class 0 as failed, class 1 as passed. This is a logistic regression. Two condition, true or false, 1 or 0. And so that by mathematical intuition. So, with 87.5% of the test samples being passed, a model that always predicts pass would achieve 85.75 accuracy. A model that will always predict pass, meaning it normally knows about pass, it has overwritten or it has ignored the fail class to normally predict 87.5% accuracy. But why is it? That's why you not obtain that? Why is that not the case? Why is that not the case? For accuracy, we're getting 89%, while since the entire data, we're finding that over 87%, 87.5% of data is the pass category. Now, this is when we cannot only rely on accuracy alone here. I we have to understand that. That's why we are not only are supposed to rely on accuracy itself. We have to explore other evolution metrics like the F1 score, precision recall function, support weighted average, and the rest. In neural networks, we'll now talk about even others like MSE or mean squared error. We're able to see that in the coming section. Now let's dive into our confusion matrix. Confusion matrix is a graphical way of representing the four particular outcomes. You have what's called true negative, false positive, false negative, and true positive. And take note, this way you want to make the emphasis on. And based on this particular four criteria is where we want to derive our precision and the recall function. So we'll do simple mathematical computation to see how has the precision function right over here been generated. Like if I take you back here, I'm having here precision as 0.44 for zeros, while recall I'm having 0.47. For one class 1, I'm getting 0.95, while the recall I'm also getting 0.95 as well. Based on the four conditions in the confusion matrix right over here, let me show you here. This is the confusion matrix itself. You're able to derive the formulas for precision and the call function together with accuracy score on our data. We have to agree that accuracy alone is not sufficient. You have to explore other ways of evaluating our matrix. Okay? And let me take you back to my document here. True negative. What does true negative means? What does true let's say true positive. What does true positive mean in our confusion matrix over here? What does true positive mean? So very simple. Just take it easy. Just take it easy. True positive means those results that has been predicted as past but are actually past. Yeah. My result in my during my testing, I'm going to get my in my Y predictions, I'm going to get those values that are actually the student have actually passed, that's label one. And in my original data, that was the testing data, okay, they're actually one, meaning they're actually passed. So this is goal. My prediction is exactly matching the actual past result. Let me show you that by example. If I go back to my data here, let me go back to my data. Originally, this is what I had. Let's take at the top. Okay, let me show you this. Just in a minute, let me show you. Okay, let me show you what's there. I want to show you where we had the original data after doing the feature engineering. Exactly, this where is it? So in my data here, I'm having the column for pass 1111 000. So during my testing, I found that my testing column is giving me 1111 0 111 1 0. It means exactly all my prediction matches exactly all my original column for the past values. So that's what true positive means. What does true positive means? Predicted result for past is actually matching the past column, okay, or the entries from the past column. For me, it's 111 for the past entry. Yeah. So that's what it means. True negative. That means okay, my algorithm has predicted for me a fail, but actually there's a fail itself. When I'm having zeros, exactly matches in what I had in my original data. Remember, I'm still testing. I'm still testing. If I go back to my data here, let me show you. I'm having zero here, zero here. So during my testing, if I print my matrix or if I print my entire data, I'll be having where in for example this column number three here, I'll be having it as zeros. For seven here, I'll be having it at zero. It means this is very true. Those predicted as failed exactly matches what's there as failed. While true positive is the inverse. Exact match for those that has been denoted as pass. Okay? So that's all about true positive and true negative. Now let's talk about the false positive and false negative. So in false negative here, FP, denoted by FP, predicted pass actually failed. It means this is an error. I predicted a column or an entry to be passed, but in real sense, that's a fail. I'm giving myself a 1, but instead, in my original data, it's a 0. So in normal case, we call it a type 1 error. Now, they have not the type 2 error, where everything is negative, false negative. It means my results that has been predicted as fail actually passed, okay, which is very wrong. So that's the inverse of false positive and false negative. So that's it all about the confusion matrix. So the confusion matrix here itself will enable us to compute the accuracy score, precision, recall function, F1 score, even with the support and the weighted average. All that will be used by some small mathematical computation. We're going to see in a few minutes. Okay. Do you have any question about the confusion matrix? Right over here, Mr. Dennis. What have we discussed? Okay, that's good. Because I'm mapping them to now what we did earlier on. It's now not much theoretical, but you can see that from our original data, you are able to map that as well. So let's just proceed then. If there's no question, now let's start with what's called accuracy itself. So if I go back to my model here, where is it? Let me show you my accuracy. So always remember accuracy will always change. We will agree because of the random state. Will shuffle every time. Like for me here, I'm having 0.8, 0.08%. I mean 0.088, meaning it's 88% accurate. Which is good, which is very good. And our test data here is 200 records out of 1000. Out of the 200, 26% were predicted as zeros, while 174 were predicted as one class. These are the past one. 174 failed were predicted as 26 of them out of the 200 entries for the testing. So let's break down each of this particular segment. What's accuracy? What is precision? What's recall? What's F1 score, support, and the others. Just follow up quickly. Let's go back to our document here. So how are we coming with accuracy? How is our model coming up with accuracy? What is the simple mathematics? How is what's happening behind the hood? Why? What's really happening? Okay. Now, accuracy is given by the sum of two positive plus two negative. I hope now you understand what those mean right over there. Two positive plus two negative divided by the total sample. I can say my total sample is 200 for testing. Okay, remember we split 20% of our data for testing. 200 out of 200. If I sum the two positive and the two negative, I'm getting 178 out of 200. So if you take 178 out of 200, we have 0.89 as the value. So if you transform that into percentage, you'll have it at 89% accurate. So ideally speaking, 178 out of 200 test sets predictions were correct. However, the severe class imbalance means this metric is misleading. So we want to explore the micro average for a fair view of what's really happening. So there's a trap here. Predicting pass for every student gives 87.5% accuracy. For you to predict pass in your data, it should give you 87.5%. That's what we show what we saw earlier on over here. In our real data, 170% of our students actually passed, while 25% of the testing data out of 200 have actually failed. But why are you getting the difference of 1 point? What's the difference? 89 divided minus 87.5, that will give you around uh, 0.15. I'm not wrong, let me see. Yes, 1.5, that is, sorry, 1.5. That's the difference. So only 1.5% percentage points below our model. This model's real value lies in its ability to identify failed students, which accuracy cannot capture. Most of my failed students, the accuracy hasn't managed to capture. Why? I ought to have something like 87% 0.5 as my overall accuracy. But for me now, I'm getting 89%. There's that slight difference. That's why we can't normally rely on accuracy itself. but it's a good way of weighing our performance of our machine learning algorithm. So accuracy is what percentage of all student predictions were correct. So we find that it's a one out of 170, out of 200, 178 of them were predicted as past students. But in real life, we only have 175 as a pass. So let's dive into more metrics. Now we will check on the precision itself. Now, precision is the quality of positive prediction. So it means, in simple terms, of all students the model predicted will pass or fail, how many actually did. In our model, after predicting 89% of my students passed or failed, in real life, how many were actual? How was the what is the exact thing? What is the truth? How many actually did passed or failed? We know it. We know it. We know it. We know that 175% in our data, original data, are those ones who have passed, while 25% of them are those who have failed. It means if it was that, it's 12%, 12.5%, while the other one is 87.5%. And you're able to see that as well. Okay, right over here. So for you to mitigate the, you can delve into more metrics. Precision, think of it like a fishing net. If you're fishing, precision measures how few wrong catches you made. You place your net to capture, you're expecting 10, but all of a sudden you've captured only 8. So that's it, the precision itself. How what's the precision on capturing a fish when you're fishing? So connecting as a fishing net. How is it generated? Precision is equal to true positive divided by sum of true positive plus false positive. Now let me show you the confusion matrix in a visual format. Let me show it right over here. Let me show you it over here. I plotted here confusion matrix for my algorithms. 0, 0, these are the true, this is the false negative, okay? 1, 1 is the true positive. You can match here 1, 1, true positive, while 1, 0 are the true negative, okay? While 0, 1s are the true, there's false positive, I mean, right over here. So this particular confusion matrix, you can map it with what we had earlier on in our data. So it's exactly what can be matched with this particular diagram. Let me show it in a few minutes. Right over here, we have the diagram. Yeah. So we have the values there inside our confusion matrix. So if you pick this particular numerical values here, like 10, 7, 169, 14, if you pick these particular values, you are able to compute the precision here by taking TP divided by the summation of TP plus FP. That will give you, for our example, let me go back to what we have here. I'm having my precision for 0 as 0.42, okay? 0.42. My recall function, I'm getting 0.59. So that's how you actually compute this particular precision function. Precision is equal to TP, okay, plus, no, TP divided by TP plus FP. And that's what we will have. So my class 0, initially I'm getting 0.59, then for my class 1 I'm getting as 0.92. So in this particular example here, you'll see here 0.42, 0.96 for class 1, 0.96 for class 0, 0.42. So if that is not clear, you can rewind back the video, okay, then you rewatch that particular section, you understand how to compute the precision itself. Now the model is very precise when predicting the past. That's 92%. but much less reliable when predicting the fail. It's giving 59%. That means for every 10 students labeled failed, roughly 4 actually passed. Out of every 10 students that were labeled failed, roughly 4 actually passed. So, high false alarm rate for failing students. And that's true in our national data. More of our students actually failed than those who passed. Now, that's how you compute the precision itself. And that's how Python or machine learning algorithm computes the precision automatically. So you don't have to do this using a calculator manually. It's being computed via the classification report itself. So that's how you come up with the precision function. Do you have any question on that, Mr. Dennis, for precision? All right, that's great. Now let's move to the next thing. That's the recall function. Recall can call it the sensitivity. Coverage of all real cases. That means of all students who actually failed or passed, how many did the model correctly identify? How many of them did my model correctly identify? Think of it like an early warning system. Recall actually measures how many at-risk students you detected. How many at-risk? That is, of all my students who actually failed or passed, how many did the model correctly identify? So I have my data. Maybe let's say for failed, how many were the model correctly identified as failed? So if I've passed, how many of them were really identified as pass? Again, based on what you have understood in the confusion matrix here, let me show you a screen 1 minute. Okay. So based on what you saw in the confusion matrix here, 0 is for false, while 1, I mean 0 is for pass. Sorry, 0 is for fail, while 1 is for pass. Same here against the predicted. In the actual against the predicted, the actual is the true one, while predicted as you can give it as predicted against the actual. 1 is the true positive. How many were actual and how many were actually predicted? So for me here, I can say 169 is the true positive. 169 of them were actually having values 111, and exactly 169 were actually predicted. So that's what I'm having as true positive in my confusion matrix over there. Don't worry, I'll share with you this particular notebook itself. So let me navigate back to what I have in my recall function. So recall, you want to take TP plus TP, okay, divided by TP plus false negative. So that's the inverse. The other one we had true positive, false positive. Then we are having true positive, false negative. So that's it. The only different. That will give you the recall result for class 0 and for class 1. 0.4%, it means only 40% of real failed students were caught. While in my model, 96% of real pass students were correctly identified, which is very true. So let me take you back to the result itself. So think of it in this particular manner. My recall function here, 0.59 and 0.92. For class 0, I had 0.95, meaning 59% of my students were actually predicted, while for class 1, 0.96 were actually predicted. So all this will help you to come up with your accuracy. Then we want to move to what's called the F score. Now the ratio of the ratio between the precision and recall function. So let's see that. Now, F1 score, you call it the balance champion. Why? When both precision and recall matter are equal, use F1 score. So F1 score is the harmonic mean of the precision and the recall function. So if for you to come up with the F1 score, we're going to find the harmonic mean of the precision and the recall function. So it basically penalizes a model that scores when well on one but poorly on the other. So it basically penalizes or mitigates in any model. Maybe if you use logistic regression or decision tree classifier, it normally penalizes any of the model that will score well in one but poorly on the other. Suppose you're testing your data, this particular model performs well in the one data other than the other one, you are able to streamline this by using checking at the F1 score. Now, what's F1 score? Is the harmonic mean of the precision and the recall function, and that's what we have it as the function here. So F1 score is 2 times precision, the value of the precision times the value of the recall, okay, divided by precision plus the recall. If you do this, it will give you the harmonic mean. So that's just the mathematical computation, what my algorithm does behind the hood. You don't have to cram this, just know how it's been derived by the code itself. Now, ideally speaking, if you have it close to 1, there's a good one. But if you have it close to 0, that's a poor one. So basically, it's between 0 and 1. 0.48 is close to 1, so that's a poor one, while 0.96 is close to 1, that's an excellent one. So that's how you interpret the F1 score itself. So we have a scale here for F1 score. Before I go to this scale, so let's check how they come up with this 0.95, 0.48. It means 2 times 0.59. Okay, so if I go back to my model here, suppose this was 0.59 times 0.49. In my first instance to 0.40 divided by 0.49 itself here plus 0.42. 0.59 is my precision. For me here, my precision here is 0.42. Okay, then my recall itself here is 0.40. So if I go back here for class 0, let me check back here for class 0, it is 0.59. I'm going to take 2 times 0.42 divided by 0.49 over 0.42 plus 0.59. That's for class 0 itself. And I'll have a value as 0.49 as my F1 score. The same applies to class 0. For class 1, that is 0.96 times 0.92 over 0.96 plus 0.92. If you do that accurately, you have a value that's 0.94. By up that point, you know what a precision mean, what I'll call is together with the F1 score. Now, hey, how do you interpret your F1 score? For me, here I'm having, for me, is a value 0.49 for class 0. What does that mean in our scale here? Any value below 0.50, that's a poor score. My model is performing poorly. And that's true. For my class 0, the model is performing well because initially we only had 25% of students being, or 12% of my students, 12.5% of my students in my data are they failed. Okay, while in but while using my model, there's that particular difference of 1.5. We subtract from there, we find that maybe my model is saying 11.5% of my students have actually failed. So my model is not doing well. That's why we're having it as a poor score. Now, between 0.5 to 0.7, you need to work on your model. Between 0.70 to 0.880 is acceptable, no doubt. Well, a good one is between 0.8 to 0.9, like what's happening in my past situation, my past scenario. My past, I'm having 0.94 as my F1 score, 0.96 as my precision, 0.92 as my recall function. So that's a good one. Though An excellent is above 0.90. That's an excellent prediction. The enormous gap that we had before between 0.48 fail and 0.95 pass reveals that the model has learned the majority of the class pass very well, but struggles with the minority, that is, the class fails. There's that aspect of from the class imbalance. My model has learned so much, perfectly fine on my pass class, while it has tend to ignore the failed class. So addressing class imbalance will improve the fail detection. And there's ways of which you can deal with the class imbalance itself. And I'll show you that in a few minutes. Now support, let's move to last three: support, micro average, and weighted average. So that's what we have over here. Support, micro average, and weighted average. Now support basically is a sample counts, huh? Like what I am having here, 17. It means out of my, okay, we all know that there were 25%, 25 of them in my data. My model has predicted 17 of them to be of class 0 or mean class failed. While out of them, 183 of them is of class pass based on my model prediction. Suppose to have in here as 25, 175, it means we would have gotten 100% as my accuracy score. 100%. Again, 100% is questionable. You remember that. Okay, now for class fail, 25 students in the test set and class 0 should be 175 in the test. While for us, we're getting 17 and 85. Not bad. Now, macro average treats fail and pass equally, while weighted average, that's 175 pass versus 25% fail, basically pass pulls results up to 0.88%. I mean, that's 88% accuracy. Then you have now the mathematical computation on how to come up with the macro average itself. What we are having over here. How is it generated, the macro average? So for my computation in my original training, I found it that 0.75 plus 0.68 divided by, no, plus 0.71 divided by 2. If we do this, we'll have the value for your average, micro average. Best metrics to use here, it gives equal weight to the underpresentable class. Like for failed class, it's underpresented. So it will give you the equal weight. To help you to counter the aspect of model underfitting or the overlooking of the minority class, the least presented class, for us here it was the fail. So to help you to mitigate that, again, if we check at the weighted average here, that's misleading. It inflates overall performance by being dominated by the majority pass class, which is 0.88, which is a good one. For us here, we are finding my weighted average as 0.91. 0.91. So that's how you interpret the support, micro average, and weighted average. So let's summarize up with the full classification report itself. I'm having a class, the position itself, the call itself, F1 score, support, and the grade. Okay, just now way of just assigning the grades to my result. Overall accuracy 10%, micro average of 0.71, weighted average at 0.88, while test size of 200 students will show you this particular grade scenarios. In my data, originally we had 25% failed, 170% pass. So if you compare each of these metrics, we all agree that accuracy alone is not sufficient. More so, if you have a class imbalance, that's why you have to look at precision, recall, and F1 scores. So for instance, precision model is far more reliable when predicting pass than fail, and you're able to see that. For recall, our model misses 6% of the fail incidents. That's the biggest weakness in that data. F1 score, we saw that huge gap confirms that the model is biased toward the majority class. It means it's giving priority or it's favoring the majority class instead of the least presented class for the fail. So there's a severe imbalance of 1 to 7 ratio. How? We saw that actually we're being told that out of my data we'll have 17. Instead, we are having 25 for the fail student. While we are having 175 for the fail, here we're being told we have 183 based on our prediction. Okay? Based on this is how our modelers predicted. We can't cut that out. It's just okay. You have to work it out with that. There's no problem with that. So this particular section here I'm sharing with you gives the summary of the formula of coming up with accuracy, precision, recall, F1 score, support, micro average, weighted average. All that has been shown using a mathematical function and what it means based on our data. Let's see the golden rules. What should you consider? What should be done? And what should be used? Like, in what scenario should you use accuracy? Okay, and why should you use it based on our student performance context? Now, when you have class imbalance, like what we're having right over here, 25 against 175, there's a class imbalance. You are going to use accuracy. Okay, so this will give you a fair representation of both pass and fail. Now, when there's class imbalance, you use accuracy. Why? This will give you a fair representation of both pass and fail classes. Second one, when classes are imbalanced, like in this particular data set, F1 or macro average, okay, accuracy alone hides the poor fail decision. Why? There's that bias and there's that particular favoritism or priority given to the pass class. That's why you have to check at F1 score and micro average. In cases where there's falsely predicting pass is costly, use the precision. Okay, and you know how you come up with the precision itself. We discussed about earlier on. So avoid telling a failing student they pass. Avoid telling a failing student they pass. So that's based on the precision. Now, in cases where the missing a failing student is costly, okay, the other one was where we're falsely predicting a pass is costly. Here we are saying when you're missing a failing student is costly, use the recall function. We'll check on that. And you have seen how that should be uh, out of our graph here. You see what's poor one, what needs to work on, what's acceptable, what's a good one, and what's an excellent. Okay, based on what you are finding out. So, when missing a failing student is costly, use recall function. Why? To catch every student who actually failed. So that's how you use or how you to interpret the precision, recall, F1 score, accuracy, micro average, and weighted average. During your data interpretation or during your report classification, you will be able to compare all this. Why? Relying only on accuracy won't be sufficient enough. You must have to check on other parameters. Otherwise, you will be having a biased model. So that's all about the evaluation matrix that you'll be using with our machine learning algorithm. So thanks so much for viewing all that. And if you have any question, you can ask Mr. Dennis.